All right, good afternoon, everyone. Welcome to class today. Trust you are managing the rains we have been having for the last couple of days and that you're all nice and dry. All right. Based on our schedule, today we should have been looking at substation fundamentals, but I think we have enough flexibility in our schedule, so it will allow me to do a couple of other things. And so today I want to try and address some issues coming out of your mid-sessional exam. All right. So that's what we'll be looking at today. First things first. I am going to assume also that you have looked at the solutions that were posted. We are gonna try our best to go through them. And if you have queries, if you have questions, if you disagree with anything there, then you now have an opportunity to have them addressed. All right, so that's our plan of action for the next 2 hours. Now I recall, I think it was Mr. Smith at the end of the test on the 24th, said that, well, queried whether or not I expected you to have finished this paper. And I want to refer you back to the message that I sent. I think it was the morning before or the day before, whenever it was sent. But I did send a message just cautioning you all to, try and get some quality rest, to take a break, and to make sure that you come to the exam with a clear mind. That, as it is water under the bridge, so I'm not going to spend much time talking about that. However, some of the errors that I saw persons making, I have to attribute them to you being tired and you not concentrating. I'm not going to raise it beyond that. Of course, was a little disappointing for me. So I decided that I would take time and go through the paper with you. All right. Before I do that, is there anyone who have a comment? Anybody who may have felt that the paper was unfair? Did you see anything that you were not exposed to? This is the time to make such a comment. All right. So I take the silence to mean that you're good. So we must just get on with it, eh? All right. And I'm going to start with question 1 because for this particular question, it's theory-based, and much of it was based on your reading assignment. Some of the stuff we did speak to as we went along in class, but some was related to your reading assignment. But I'll go through it. And one of the reasons I spoke about persons just not concentrating, the question asks for you to sketch and explain the difference between short, medium, and long lines, and explain how these differences impact the analysis of systems consisting of these classifications. All right. And so the majority of persons who offered a response to this question were quite eloquent in describing the length of the line, the 80 kilometers, the 240 and over, all of that. You're pretty good with that. But of course, and also indicating, for example, the short line, was only considering the inductive reactance and the resistance, the medium, put in the shunt capacitances. But of course, for the long line, we're dealing with distributed parameters. All right. So for the short and medium, we're dealing with lumped parameters. For the long line, distributed parameters. So once you had spoken about those differences, then you would have received your 4 out of the 8. But the other part of the question asks that you should explain how these differences impact the analysis of systems, right, with these classifications. If my memory serves me right, there was only one individual who attempted or seemed to have even seen that part of the question. So what we're looking for here is that you would have spoken to the fact that for transient analysis that you would require long line classification. And we went into that, the wave theory would have been applied to the distributed parameters. I may just segue a bit here because in question 4, where we dealt with the transients, persons converted the inductance and capacitance per unit length to lumped values. Yes? So you had the inductance per unit length, you had the capacitance per unit length. They multiplied it by the length of the line and lumped it. And what that told me is that there wasn't much understanding in terms of the fact that you needed the length, the capacitance per unit length and inductance per unit length to do the transient analysis. So the distributed parameters are required for that. So it was a little disappointing when persons converted that to lump parameters. But coming back to question 1, that's what I was expecting. Short lines for quick analysis, for your short and your medium, for steady state analysis. The short for quick analysis, for your medium, you'll be carrying out more detailed analysis to look at losses and that sort of thing. And then for the long lines, you're dealing with the transient behavior of the lines. So the second part of the question would have given you your additional 4 points. So those who would have gotten the 4 would have been based on the description. However detailed you made that description, you got your 4 points, but you needed to have spoken about the use of these lines and how and the benefit or how we analyze circuits consisting of them. All right, part B. Spoke about contingencies, and I think most persons have had an idea. Those who attempted it had an idea of what a contingency is. But let us, students, let us try and ensure that we do not try to stretch some of these things beyond. Well, to be honest with you, I'm not sure what was being done, but you went beyond the basic meanings that was expected. And simply put, a contingency is that plan that would be implemented based on possible failures. So you have a contingency plan, but the N-1 and N- contingency is the assessment of the system's stability during the loss of 1 or 2 major pieces of equipment. All right. I was disappointed with this particular question. Not so much because of some of the stuff that was written, but for a number of students, I saw where they repeated the same error. And I'm not going to, well, I'm not going to say how it is that you ended up writing the wrong thing. I leave that to you and your conscience, But I was very disappointed with that one. And you had the opportunity, yes, to use your own words. There's nothing that you had to be extracting from a text or from your notes. Just discuss it. What's the importance? So the contingency is really about testing the stability of the system under these conditions, whether you lose one or two pieces of critical equipment or pieces or sections of your network. Sections there would speak to the loss of lines, yeah? Or you lose a transformer and a line. But having looked at what was presented, it gave some clarity for what was done in that lab test, because some persons weren't sure what to do when I mentioned N-1 or N-2 contingency. So that, I believe, was an easy 14 marks, but All right, so let's come now to question 2. Do you have any comments or questions regarding question 1? Anybody? All right. So question 2. So we have a network here. You have 3 different, I think there were 3 voltage levels. But anyway, we'll get to that. What was key, however, and I think this was an error that I saw repeated by many students. The base voltage, yes, must be indicated points.
Dr. Isaacs?
Yes.
I'm seeing a blank screen, sir. Are you showing something at the moment, or are you going to write on the screen?
You should be seeing a blank screen.
Okay, sir.
All right. So you're seeing a network. And, well, going back to what I was saying, the base voltage must be specified at a particular point in the network. All right. So what you are given the base MVA. So S base 100 MVA. All right. Now you need to specify what your VBase is and where that VBase would be. So you can start by saying let VBase be 69. So VBase, you want to start with VBase. Let us say 69 kV on the line. So 69. Come on, don't do that to me now. All right, so VBase is 69 kV on the line. All right, now once you have specified that, as we said, when you go across the transformer, that VBase1 over VBase2 must be equal to V1 over V2, which is the same as N1 over N2. So the base voltages must be, the ratio of the base voltages must be the same as the turns ratio of the transformer. So when you go across transformers. So I saw persons who may have started with the 69 on the line. Yes, they carried that 69 to the primary side of the transformer. So they carried it also when looking at generator one. All right. All right. So let's get started. So for G1, so we're now converting. All right. For G1, these are the new values. Right. We'd have the new base over the old times the old base voltage. And if you look at the network, the base voltage there was 14K. So it's 14 over 13.8. And it is 13.8 because, as I said, this must be true. All right, so we have a 69 13.8 transformer. Yes. So on the generator side, it will be 13.8 squared. All right. Times J0.2. All right, and that works out to J0.1029. All right. Now, I'm trying to touch everything because I don't want us to make the same errors going forward. No, students. I think for those with whom I have been associated for some time, you know my position on rounding off. So for those students who chose to round this off to J0.10, right, you would have lost a half a mark. And I at this stage, you know, I'm not even going to feel too sorry for you. All right. So the answer is J0.1029 and not J0.1. So that's for your generator. For the transformer, so that's T1. Yes. ZT1 would be J0.1. All right. The very theory regarding per unit is centered around the transformer. So once this is true, once that is true, all right, for the most, all we need to be focusing on really would be the SBS values. Yeah? So we're just multiplying that by 100 over 150. And that gives us 0.0666. And we can put that recurring, or we can put up another 6, 7. All right. Again, if you want to round this off to 0.067, more power to you, but it's going to be less marks at the same time. All right. Now, when we go to the line, we have Z base, which is going to be V base squared over S base. And this is true whether or not we're dealing with a 3-phase network or a single-phase network. I think one person had asked me about this. All right. And this gives us 69 squared over 100, which is equal to 47.61 ohms. And of course, for each of the line, for line one, that would be 2 plus J5 over 47.61. And for line 2, that's 1 plus J8 over 47.61. Now, students, I was very troubled with this particular question. I was very troubled because there are at least 8, could be about 10, yeah, must be 8 to 10 students who, for whatever reason, had 47.61 divided by 2 plus J5. All right, and also 47.61 over 1 plus J8. And the reason I'm troubled is that this sort of error I would accept, if it was an individual who did this. But when I see it being repeated by a number of students, and I took note of the fact that a couple of the persons who made this error were also lab partners, it's a bit of a concern, right? You must know the reason this error was repeated among you, all right? But it was cause for concern, all right? So this is 0.042008. Let's get rid of this. Plus J 0.10502. All right. And this one was 0.021004 plus J 0.16803. Right. Again, we also had some rounding issues with this, but I think by now the point is made and you understand how we treat with this. Any questions so far?
Yes, sir. I have one.
Go ahead.
Let's say I put the lines in parallel and I just work it one time in the parallel state. Is it the same thing?
Go again, Amaja. I didn't hear you clearly.
I'm saying that let's say I work the transmission lines in parallel. Would that be the same thing?
Well, I realize that you did that for, I think you did it for both the load and the lines, right? But look at what the question asked for. I didn't penalize you, severely, but the question asks that you draw the equivalent per unit diagram. You with me? The equivalent per unit diagram does not have the lines combined. So you were required to calculate both, but not combine them in parallel. You would combine them in parallel for part C, which asks you for the active power dissipated by the transmission lines. Yes, but certainly not at this stage where you needed to redraw the diagrams.
Okay.
All right. And then for T2, that would be J 0.12 times 100 over 75. All right. And that, of course, is J 0.16. Okay. Now, here is where I got even more concerned, because when we dealt with the loads for ZB, if you look at that particular transformer, it's a 6924. So on the 69 side, it is connected to the line. Now, because it is connected to the line and it would have the same base voltage as the line, the turns ratio, as we mentioned earlier, all right? This being true means that the base voltage on the loads would be 24. So ZB for the loads would be 24 kilovolts. All right. So V, what did I say? Not ZB, VB. All right. So VB for your lines would be 24. All right. So that's V. And so ZB would be 24 squared over 100, which is 5.76. Now, I was saying that I was more concerned, especially based on what I just mentioned with the lines. The same persons who put 47.6 divided by 1 plus J8 and 2 plus J5. For the loads, they actually put in the 0.4761 and the 0.19044. They actually divided that by the 5.76. And so I couldn't understand how it is they were getting it correct at this point. But for the lines, they were putting the reciprocal. And, you know, I can't explain it, but I just, again, have to assume that, you know, persons were tired and made that error, even though I am also concerned that so many persons were making the same error and at the same time was getting this part correct. All right. But as I said, you will have to decide the basis on which that particular error was repeated by so many persons. All right. 38088 over 5.76. So, all right. So you have the value. So I'm not really going to write this out. And for T3, the voltages are the same. It is the same rating as the system base. So it remains as J0.12. Okay. So it remains as J0.12. And then finally, in terms of conversion, next we look at G2. So for G2, all right, so for G2, we have J0.2 times 100 over 150. And again, based on turns ratio, the base voltage on the generator side, would be 13.8. Okay, so because it's 13.8 and the generator here is at 13.2, we'd have 13.2 over 13.8 all squared. All right, and that gives us J0.1219912. Okay. Again, students, I mean, each of these conversions I gave you a mark. All right. But in one instance, I had to go back and double check my calculator to see if I had done something wrong, because I saw for more than one student, they had this statement, just as I have it written there. All right. But this final answer was incorrect. And I saw the incorrect answer on more than one paper. I hope you understand where I'm getting at, what I'm getting at by saying this. All right. There's no way I am expecting students of your caliber to be writing down something like this, writing down this expression, getting the wrong answer, and then I see more than one of you writing the same wrong answer. All right. It's a concern for me. And, you know, well, I'm encouraging you to just focus on your own work. All right. So once you have put these in, then you would get your 4 marks. To draw the final circuit, you get only 2 marks, but the other 2 conversions that you would have to make, because you're doing the equivalent per unit, you would also have to do the voltage conversion for generators 1 and 2. And so for G1, it would be 14 over 13.8. And for G2, it would be 13.2 over 13.8. All right. And you'll put those in. I think this one worked out to 1.0145. And so for some of you may have seen me just circle the generator because you had no value there. You just put back the generator without the value. All right. So you have to deal with both the reactance and the voltage for your generator. Okay. If you look throughout the network, only the generators have the voltage on them. All the other pieces of equipment, you're just having impedance or reactance as well as, right? As well as rating. But for the generators, you have the voltage. So you need to put these in. All right. So 9.5, 6.5, 2.2. All right. Any questions? All right. All right. So there are no questions. What I'm going to do is to therefore go to part B, and I'm going to simplify the network. So Lamanja had asked earlier about the combining the lines. All right. I'm going to do that. So I'm going to combine the lines. I'm also going to combine the transformer and the loads. All right. So the simplified network, all right, simplified network would then look something like this. And then this would be our bus bar for the loads and the transformer. We'll have that. And then over here, we'll have the transformer and the generator. Okay. And from the equivalent diagram, you would have had those earth points. And then we have our generator over here, and we have another earth point. Now, the fact that we have these earth points, yes, means that basically I can remove them, no? And if we remove them and just join them, because they're at a common point, what we have is a 2-mesh circuit. All right. So this would have been at 1.0145. And over here we have the 0.956522. Okay, we have the transformer and the generator here. All right. That was J0.241992. And up here we have J0.235, etc. And beside that we have 0.01876, etc. Over here we have the load, J0.182, etc. and 0.055. So students, this is what I was expecting from you. So what you would need to do at this stage, you choose the method you want to use, whether you want to use mesh analysis, whether you want to use nodal analysis, totally up to you. All right. So if we use mesh, all right, I1, I2, yes. And of course, you would have done this in networks too. So you write your mesh equation, or you just write your matrices, okay, and you solve them. So in solving, I don't think I need to go through the networks for this. You should be okay with that. So I1 comes out to 1.74, 37. And I hope I don't get myself into too much trouble, but I think Mr. Jeffrey was the only one who went this far. Minor error, which I didn't penalize too much, but there's a minor error in the matrix equation. All right. And I2 was 3.2068. 68188. Okay. This was at minus 78.69. All right. Now, I2, if you go back to the original circuit, I2 would have been the current going towards the, or going through the combined load, which is going through this, right? Those two. So we could find I load 1, which is what you're asked for. I load 1 would be I2, which we just found, times Z2 over Z1 plus Z2. These are L1 and L2. All right. So you use current division, and that would be your 8 marks. All right. And then for the 5 marks, you're asked for the power dissipated. Of course, we know that the power P would be I squared R. Yes. So from the combined lines, yes, from the combined lines, you would have had RT. So you have I squared RT. But before you do that, what you're using is I1. But I1 is in per unit. So you need to convert that to I actual. Okay, where the base, of course, I base would be equal to 100 over root 369. Since we're dealing with a line, the base voltage would have been the 69, since we know that the 69 is on the line. All right, now we find the actual current. Yes, we square that. Oh, well, that should have been 1.4, not 1.7. All right, so what we have there, so just correct that on the on what I had sent you. All right, so it should be I actual is 1.44591. So that is what we are squaring and multiplying by R. Okay, and R is what we had here. Okay, that was the combined resistance for the lines. All right, so we didn't need to calculate anything again because we only included reactances from the transformer. So the R there would only be related to the lines. Okay, so just correct that for me on the solution. All right, and that would be your 27 marks. Any questions? Any concerns? All right. So let's look at question 3. Now, question 3. Hold on, just let me. All right, so you're asked to find the phase currents at the fault point and the phase voltages at the fault point. I recall, I think it was Mr. Porter. Correct me if I'm wrong, Mr. Porter. You had asked a question some time ago regarding, I think it was lab 1. And I responded to you by saying that what would have been of greater concern is whether or not you had all the information needed, because I had given you more than you really required, which is exactly what we did in question number 3. We gave you more information than you really needed. And I'm not going to cast any aspersions here, but I saw too many persons, based on the information that I gave you, who thought it necessary to put in a series parallel network. So you put all the networks in parallel, right? Which of course would represent a double line to ground fault. Right? What you were asked here is for a line-to-line fault. And given a line-to-line fault, it means that you're only dealing with the positive and the negative sequence networks. So you have here your positive sequence, and you're connecting that with your negative sequence. And the key thing here, students, is that, as I have said on many occasions, the currents must be going out. All right? So you have your 1 per unit. You have your 0.1563. And of course, here you have your 1644. Now, I just mentioned that some persons use the 0 sequence and put them all in parallel to make a series parallel network, which, as I said, would have been a double line to ground fault. But there are also persons who put them in series to make a line to ground fault. I can't say, obviously I don't know, what would have caused that type of error. I really don't know what would have caused that type of error. But people make errors. I'm going to submit, however, that the possibility is that persons were just mentally tired, which is why those sort of errors were made. However, of greatest concern to me was the fact that I am dealing with level 4 students. And there were a number of persons who drew this circuit. They drew this circuit, but then went ahead and calculated these 2 reactances in parallel. That for me was the most scary. All right. So I mentioned Mr. Smith's comment at the beginning of today because he said that he queried whether or not I expected y'all to finish this paper. But I trust you would recognize here that as slow as I am going with this paper, we have still not gone an hour yet. All right. Point is, this paper could easily have been completed in 2 hours. All right. Now you have these two circuits in where they are connected in parallel, but they form a series circuit. Okay. And so I1 would be equal to minus I2. All right. So you can find, well, I'm just going to go through it since that's what I am doing here today. So I1, which is equal to minus I2, is equal to 1 over J 0.3207. All right, which gives us minus J 3.11818. And of course, I2 would therefore be equal to the negative of that. Now, students, another thing I want to mention here, I am not going to dictate and I'm not going to insist on how you represent these currents. I am perfectly comfortable with you leaving it in rectangular form until you have gotten to the final answer, then you put it into polar form. All right? Somebody wants to make a comment?
You know how I say it, right? I just put Michael Jones here.
Okay. So many persons at this stage chose to put it into polar form. As I said, it's not something I'm going to dictate. That is something you can make a decision on. But I am, however, suggesting that converting at this stage to polar form will make your calculations a little more challenging. All right. But, you know, that's just my experience. I2, therefore, is J 3.11818. All right. Which means that A, B, C is equal to T into 0, 1, 2. All right. There's no zero sequence. Okay. And once you have found this, which gives you 0, 5.485 at 180. All right. And 5.4085 at 0. All right. So based on what we have here, it tells you that the currents are going in opposite direction. All right. And these are things that I expect you to be able to pick up when you are doing these problems. Because persons were getting some angles that were not 180 degrees apart, but based on the circuit that you have drawn, it would have been. All right, because they are going in opposite directions. Okay. So that's something that I think you need to pay attention to going forward. Okay. All right. Whoops. Sorry about that. All right, so let's go back to that. Okay. So once you have done that and you have found the base, we all know to find the base current. We calculate, we know that IA, because the question asked you for the actual current. So IA is 0, IB 2.2596 at 180 kiloamperes. And IC would be equal to that at 0 degrees, all kiloamperes. Okay. And then for part B, part 2 of that. You have your V1, which is 1 minus I1 Z1. And of course, V2, which is equal to 0 minus I2 Z2. And these are things that I have emphasized. Yes. In both instances, you'll get a value of 0.516. Okay. All right, so you get the same value, 0.5126285. Okay. 0.5126285. All right. 5126285. Okay. So you get the same for that. All right. And once you have multiplied that by T and multiply that by the base voltage, right? You're told it's a 138 kV transmission line. Then you'll get your 141.49. That's on phase A. And then you would get 70.74 at 180. This is at 0. And 70.74 at minus 180. All right. Which is what we'd expect. You know, under those fault conditions, you'll have voltage collapse. Okay. So that's your mark for, oh, that's your 16 marks. All right. So let's see how we go after the other 14. All right. Part B. I don't think many persons attempted this. I think, again, only one person I recall getting this correct. The reason that you would have a difference in the two, I mean, I've said it up front in the question that under normal circumstances, the zero sequence will be larger. All right. But for this, the question is, why would it be smaller? Based on where the fault is, the easiest explanation is that the network consists of either star or delta transformers. In other words, there are parts of the network where zero sequence current would not be allowed to flow. And so because of the segmentation of the network, yes, you would not encounter the zero sequence reactance. So that would be the simple answer that I was looking for where that is concerned. All right. I think we have spoken about C, so you figure that out. All right. I put this on the paper because well, it was on the paper before, because I had anticipated that you would have been able to get that from your lab exercise. Right. So this was really just testing to see whether or not you had done your work in the lab. All right, Mr. Dwyer, can you mute your mic, please? Thanks. Yes, Mr. Burns, I see your hand. Okay.
Yes, sir. Just confirming. So the last two values would have represented the phase voltages that were supposed to be equal.
Yes.
Okay. So the direction of the last one is supposed to be negative, though.
Go again. 70.74 at 180 and 70.74 at minus 180.
Okay. All right. Thanks.
Remember what I said earlier, that at the end of the question, then you can put it into polar. All right.
Question, sir. For the question from theory, I was getting that VB and VC should be equal to each other. During the calculations, I noticed that when you have a value for V1 and V2, they are close but not similar. And depending on the decimal that you entered, the negative sign on the voltage angle would be affected. So in the case...
Go again. I missed you.
All right, so the value that I calculated for V1 and V2 during the exam, I got the final two decimal points. One was 25 and the other was 248. And when working the question, I rounded it so both decimals would have the same value. And I got the angle, like I got VB and VC to be equal. But if I had used the exact value from the calculator, then I would have gotten the minus sign as you have.
Well, what you would have gotten, well, I can't speak too much about the rounding of values. I can't, right? However, I do recall you getting the 5126. And then I think you got 0.5, was it 0.50 something? Is that the case? Was that the case? Sir Ramsey?
Yes, sir. Like the 7 decimal place, there was some...
No, man, you didn't go down that far. I don't recall that. But well, you know what? It was 40 odd papers, so maybe I am mixing you up with somebody. But there were a couple persons who had 0.51263 and then 0.50 something. And I just couldn't understand, how they were getting those values. As I said, I don't know. So is it that? But I don't recall penalizing you, Mr. Ramsey.
I'm not sure, sir. I was just
You got the 6 points, didn't you?
I'm not sure.
I'm telling you got the 6 points.
Okay, sir.
You weren't penalized. I didn't penalize you. I'm sure you got the 16 marks for that question.
Okay, sir.
Yeah, but you can look back and let me know. I don't recall penalizing you, but if I did, then we can address that. All right.
Excuse me, Dr. Isaacs. Sir, for the theory part of this question, I made a mistake and wrote it on the wrong folder leaf. And I'm just noticing after submission that I put it in number 1 by accident, the theory.
You sure I didn't look at it?
I'm not sure, sir. I didn't.
I'm almost sure I did. I think you had it at the end of the paper.
Yes, sir.
It was the last sheet that you submitted.
So actually, it's the first sheet that I submitted.
Well, listen to my response regarding the theory and tell me if what you have coincide, and then we can look back at it. Is that a plan?
All right, sir.
Okay. So as I was saying, for the active and reactive power, I expected you to speak to the fact that the active, whilst they may have impacts on both load angle, but the active impacts more substantially the load angle, and the reactive, the voltages. That's all I was expecting. Not more than that. All right. That's as simple as that. So I really, in these instances, because I said what I was doing is testing whether or not you had done the work in the lab. These for me were, the giveaway marks on the paper. Part D would have been something that you ought to have looked at in your theory for that lab. So part D, when you look at methods used to correct over voltage or under voltage, you had already indicated in the lab based on what we tested in the lab, you would have looked at capacitor banks, right? Now, persons were mentioning power factor correction, which has nothing to do with what what we are dealing with here. It's capacitor banks, and you have been talking about switch capacitor banks. The only reason we use switch capacitors is that from time to time we may need to reduce the capacitance or increase the capacitance. So in other words, the switch capacitor banks are variable capacitances. But in some instances where there is a constant low voltage situation, instead of using switched capacitors, we use fixed units. So there would be a fixed value of capacitance that is being injected into the system, or VARs that are being injected into the system. All right. So you have capacitor. You can use transformer tapping, or you can use make the adjustment through generator excitation. So you can either use generators, transformers, or your capacitors. So that's what I was looking at and looking for. And as I said, these for me were the giveaway 12 marks on the paper. All right. Because I figured once you had done your lab, then you should have been able to easily complete that one. And then finally, students, if there are no more questions on this, I'll just go to number 4. All right. Question number 4. What do I say about question 4? Question number 4. A number of persons ran into problems where calculating mu L and mu C were concerned. Once you converted the distributed capacitance and inductance to lumped values, if you converted them to the lumped values, you are automatically going to get mu L and mu C wrong. All right, because mu L and mu C are based on the distributed parameters. So if you multiply it by the 5,000 and the 9,000, you're automatically going to get mu L and mu C wrong, and by extension, tau L and tau C. All right? So calculating the speed for the line, it is 3 times 10 to the 8. For the cable, it is 2 times 10 to the 8 meters per second. Based on the lengths that I gave you, the times would have been 30 microseconds and 25 microseconds. Yes.
Could you repeat what you said about mu L and mu C regarding the 5,000 and 9,000, sir?
I'm saying once you convert the distributed parameters, which you are given in the question, once you convert them to the lumped value, mu L and mu C would be incorrect. So some persons went ahead and calculated L by multiplying the distributed value there by 9,000, and then C for the line by 9,000, L for the cable by 5,000, C for the cable by 5,000. Once you do that, then your speeds are going to be incorrect, because the speeds are dependent on the distributed value, not the lumped value.
Okay, sir, I understand.
Cool. All right, so we have tau L and tau C as 30 and 25. So of course, I don't think I need to, go into how we calculate those. All right, but we have those times, and we find ZL and ZC. All right, ZL 151.515 and ZC as 40. And so the question now asks, Let me find the question. The question now asks, 1, what is the impedance of the load that would prevent reflection? Oh, I haven't done part yet. I'll come to that. What is the impedance of the load that would prevent reflection? All right. So for your 2 marks, you just say 40 ohms. Yes. And then what is the impedance of the generator that will ensure complete reflection at the line generator junction? You say 0, you get your 2 marks. So what I was expecting, students, is that you have a load value. So I am sort of teasing you up. I give you the load value, so you now have it as 40. You have the generator as 0. What I couldn't understand is why persons, I give you as 40, but you went ahead in order to complicate the thing and said, assuming load value of 100, you're adding unnecessary complications. But whilst you assumed the value for load, there was no such assumption for the generator. So persons used the 0, but chose not to use the 40, and I just couldn't figure out why. All right. Now, you have calculated the coefficients. So alpha was minus 0.58228. And students, you know what? And I'm repeating it because I am going to be very blunt now, right? I have been skirting around it since I started speaking, but I'm going to be very blunt with you because as a lecturer, I take no pleasure in this type of performance, right? There is no joy that I take from 2 students of a class of 40 odd. 2 students from a class of 40 odd being able to get over 50% for my exam. Now, if it is, and this is your opportunity, you know. When I'm finished here, I open the floor if you wanna, yeah. If it is that I am giving you stuff that is not representative of the material that I have been teaching, let me know, right? But well, we're going to have a discussion as to what the problem really is, because we can't continue like this. This is no the point of inflection. This is where we're going to have a change direction about how we're doing what we're doing. All right. You're not doing Isaacs, you're doing power systems. Right? I know it's not easy. I know it's not an easy subject. But I have taught most of you in networks too, and I know that you are better than this. And so for that reason, because I know that you are better than this, I am not even moved to make any form of overtures in terms of helping to improve the grades, because this is not really a true reflection. And I'm just going to leave it there. And I hope for most of you, right, it would be a source of motivation in terms of how you treat with the second half of the module. All right. So I come back now to what I was saying in terms of being blunt, because I saw too many instances of copying. And not just copying, but copying absolute nonsense. What am I talking about with question 4? How is it that students at the University of Technology, year level 4 students, the first equation you wrote is ZC minus ZL over ZC plus ZL to be equal to minus 0.58228. And then the next equation you write is ZL minus ZC over the same denominator, but you get 0.4 something. Explain that to me. And I saw several students doing it. It's not one. Where I could, when I saw it the first time, I said, well, maybe it's exam pressure. But too many persons were succumbing to the pressure. You have the same denominator, the same numerator, with the exception that the two values are are switched. Yes. And persons are writing two different numeric values. But as I said, if it was one, I would say okay. And I'd overlook it and possibly give the mark, because I say it's exam pressure. But I say the same incorrect thing. Basic math. Why do we need to copy that? Basic math. But I will not belabor the point. So we got the positive. So alpha LC is equal to the negative of alpha CL. So the minus 0.58 would be 0.58. And of course, you add 1 to that. So I'm going to just stop share screen, and I'm going to bring up because I in terms of the document or my pen is not that screen friendly at the moment. So let me go for the PDF, right? So we can look at the PDF. All right, so I'll get the PDF here. So instead of all the crisscrossing that was happening, right? Instead of all the crisscrossing that was happening, this is all I needed from you. Everybody seeing the screen, I hope. All right? This is all I was expecting. So because there is no reflection, seeing that you are using 40, then it means that everything that comes to the cable load junction, yes, that came to that point would continue to the load. There'd be no reflection. Right? And Mr. Smith, forgive me for continuing to use your reference. But the moment you told me that the paper was too long, I realized that, you were in trouble. Because but then when I looked at the solution and saw that persons were, coming back with raise in this direction, then I knew that, we had a problem. All right. So this is what I expected. And you would have gotten your how much should I give for this now? You would have gotten I think with this, you got 12 marks. It's 12. No, you got 11 marks. And then for the showing the voltages, then you get the additional 6 to bring you up to 17. All right. So this is what I expected from you for the 12 marks, and then for the voltage and cable, I've put the
Sir.
Yes.
Sorry to cut you, sir. I don't see here in the question where it asks for the Bewley lattice diagram, sir.
You can't draw the other part without the Bewley lattice, sir.
Question, sir.
Yes.
Sir, what if you only use the cable line section of the Bewley lattice? Sir, only drew the cable to line section half of the Bewley lattice and left off the cable to load section.
But there's nothing there for cable to load. I have not drawn anything for cable to load, you know.
All right, sorry,
The
transmission from for the
No, that would have been over here.
line to cable. Or
This
line to
would have-
cable, sir. Transmission from line to cable.
Transmission from line to cable.
Yes, sir. The cable section of the Bewley lattice. I only drew the line section since that's what the question asks for.
No, the question didn't ask for that. The question asked for the middle of the line and cable. That's what the question asked for. Are you seeing that? Huh?
Yes, sir.
So it wasn't just for the line. So there isn't much that you could have left off. You with me?
Yes, sir.
So the query that was just raised as to not being asked for the Bewley lattice. I mean, you need the Bewley lattice in order to draw the voltage graph. So for the voltage graph, what am I looking for? Because you are dealing with the middle of the line, I expect that you would start seeing the 1 per unit at 15 microseconds. And then 30 microseconds later, you would have been hit with the minus 0.58. So of course it comes down to that, yes. And then at 75, it goes back to 1 per unit. And then it comes down to a lower value. And I trust if you took careful note of what is happening here, what you would find is that the voltage on the line would then go back up to 1 per unit. It would come back down, but it will not go all the way down to where it's coming from, yeah? And then it would go back to 1 per unit, yes? Then it would come down. So in other words, what you are seeing here is that the line is charging. That's the point. And you would also note for the cable, right? Each time a ray comes across in the cable's voltage is also increasing. So the cable is also coming up to 1 per unit, all right? Which comes back to what we presented in terms of the theory that, and we use the terminology in the industry where we talk about line charging. So you talk about charging the line, yeah? This is really what is happening, all right? So the voltage or the 1 per unit or the system voltage is not seen immediately across the line. Of course, in terms of our ability as humans to detect what is happening, that would be impossible. As far as we are concerned, you turn on the breaker and you get the system voltage across the line. But I'm saying that that's not the case. All right? Yes, Mr. Burns.
Yes, sir. Regarding an assignment, the assignment 3, I noticed that the graph for the cable was just going up, and I assume it was because that there was no negative value in the cable, no reflection. So, but I noticed that you're saying that the graph is supposed to look similar to the graph in the line.
I didn't say that. I'm saying the cable is also increasing. That's all I said. I didn't say it has to look similar. I didn't say that. I said the voltage in the cable is also increasing.
Okay.
All right. In this instance, the values are coincidental, or coinciding rather. Yes. But no, please. If that's what you heard, please get that from your head. All I'm saying is that they are both increasing. All right, because
Yes,
we could have had reflection as a result of the load. depending on the impedance of the load. So if the load had a impedance which was lower than the cable, then the reflection would have been negative. You with me? And that negative reflection would have then caused the voltage on the cable to drop.
Okay.
Right? So it would drop, but it would go back up, drop a little more, go back up. So that would cause the increase to be a little more staggered, so to speak. Yes?
Yes, sir.
But because we have terminated it, and this goes back to what we did in networks 2, when we're talking about characteristic impedance. Yes? And one of the things we said then was that depending on the industry you're in, then we call this impedance, we give it different names. So in transients, power system transients, these impedances that we're talking about, we refer to them as a surge impedance.
Right.
All right. But it's the same principle.
Yeah,
All right.
yes, sir.
Okay. So students, yeah, I'm the lecturer, so I'm gonna say it. I don't think this paper was beyond your capacity, and I'm not saying this to beat you up. I'm not saying it to beat you up. I want you to really appreciate the fact that, listen, you know, and I hope I don't make a mess of the terminologies, but you could easily have, what want to say, bills this, is it, go? Bills may be a bit, you know, maybe higher of an expectation, but you could have done much better than what happened. I believe you are better than this, and I expect to see some improvement going forward. All right. The other thing I did mention, looking at question 3, especially with this question, this part. Listen. I will never tell you how to express yourself mathematically. We all see math differently. If I tell you how I see numbers, then maybe you'll go and find a place for me on Ward 21, all right? But we all see math differently. But when you use the math that you are comfortable with, please ensure that you are accurate. A couple of students I saw were using some matrix equations, which are correct. You know, I had no problem with it. What I was disappointed with is that in your assignment, in the assignment that I gave you, the same error was made, and I pointed out the error in the assignment, and then the same error was repeated in the exam. What do you think it made me feel? Of course, I'm going to penalize you, but at the same time, that shouldn't be happening. Why are you going to repeat the same error? Why you think I won't see it? So power students, yeah, that's it from me today. I'm not gonna do anything new. As I said, this is your opportunity to express your concerns. You know, if there needs to be an adjustment in how we do what we do, they will hear it. But certainly, you know, some things will have to change as we move forward.
Good afternoon, sir. It's Ricardo speaking. In terms of consultation hours, I don't know if you are providing those for this semester.
Consultation?
Yes, sir.
there is no formal period of consultation, but a number of your colleagues have reached out to me via Schoology. They have sent messages. They have queried things about the material, and I have responded. I think, yeah, I think I have responded. So that's how I operate in this space. Now and again, I'm on campus, but yeah, I'm hardly here. But now and again, I do come on campus. If I am here, then fine. You can come by.
Okay, sir.
But I'm telling you, you remember how I operate in the power lab. I was afraid of a cough. So I'm not sure how me and the COVID and you all will manage. But if I am here, you can come by. All right.
I noticed, sir.
Okay. Yes, Mr. Burns. Mr. Burns, your hand raised?
Oh no, that was from before. You already responded.
Oh, okay. Yes, Mr. Adams.
Yes, sir. As it relates to the lab, sir, regarding certain stuff we should know from the lab, sir. And for example, if we get like a low grade from the lab, sir, then how would we like grasp that knowledge that we should have known from the lab, sir?
All right, fair question. Note, however, that the issue with what was it? It was question 3, Question 3. Yes, question 3, C and D. The issue you had wasn't a matter of not getting the information from the lab. There was a fundamental error made by several students. As a matter of fact, I think even before the exam, right, I spoke about it. So I spoke about the issue regarding load angle and phase voltage and bus voltage. So I spoke about that. I then went on after the lab and documented it. After I marked the lab, I documented it. But I did speak to it. And the reason I spoke to it in the class before the exam, yes, is because I knew that it was on the paper coming up on the Saturday. So if you go back to the lecture, when was that? The 21st or 20th, somewhere there. 21st of October. If you go back to that lecture, I did speak about load angles. So let us not get it the word that's coming. I don't know if I'm so anyway. Let's not get it twisted, eh? I am not here to try and catch you out because you have not done something. I started marking the labs before the exam, and based on what I saw on those, I decided to speak to the class. So I came and I spoke about the relationship between the two, and then I went and marked the lab and then put it in writing. All right. So yes, you may have that concern, but at the same time, as a responsible member of academic staff, I think I'm a responsible lecturer, I made sure that I raised the matter and tried to provide some clarity on it before you sat the exam. So it's not that you didn't have the knowledge, but it was something that ought to have been solidified by the lab. But persons were reading or looking at the phase angle instead of the load angle. The load angle was there on the network. But for whatever reason, yes, for whatever reason, persons just opt, and I don't, again, Mr. Adams, I am making an assumption here, so let me declare my hand. I am assuming that persons were persuaded to go along that path based on input or suggestions from somebody in the class or in the group that that persons may look up to in terms of their own abilities. All right. So somebody who you think no, they may have said, no man, do this, and everybody just do it. And I want you to walk back from that as a group. Yes. When you leave here and you go out there, understand that you will not have the opportunity to call your brethren at another company to ask him, how me do this again. You'll have to stand on your own 2 feet as an engineer. All right? And that is part of the training that and outlook that I need you to have. Right? It can't be based on where Mr. Dwyer, I think, or Mr. Francis. Mr. Francis, Mr. Francis is a good student. So him tell you, no man, it's not Delta. No man, Francis, all right. You go and do your own research and be confident in what you're doing. All right. And I made the point that among the students who got it right were the students who were not working in groups. They were by themselves. So, let's not get it mixed up. Although I said that it would have been something you got from your lab, based on what I knew, I decided to come and speak to you about it before we went into the exam. All right?
Yes, sir.
No problem. All right. Any other concern, query? Anybody else?
Excuse me, sir.
Yeah, man, go ahead.
About the recording for last class.
Yeah, somebody just asked. I think I may have responded to them privately.
Oh, okay, sir.
No, well, I shouldn't have. I should have responded publicly. The recording, it wasn't done. We didn't upload that recording.
Okay.
I'm trying to remember why. Anyway, yeah, that one wasn't uploaded.
And another thing as well, sir. When will we get to see the overall of what we have done for the mid-session now?
So you haven't been able to access it?
To see the work, the grades?
No, sir, we haven't.
No, man, I'm sure I did that from yesterday. Didn't I?
We're not seeing anything.
Sir, I'm not seeing anything either.
We only see
You're not seeing the grade?
No, sir.
Just
Oh.
the solution paper, sir.
Oh, yeah, I think I know why. It's oh, okay. Okay. Where are we now? Mid-sessional exam. Okay. So here I am thinking that you had seen it. Oh. Okay, let me correct that. Today is what? 3rd. All right, see if you can access it now, please. 11th. Hold on. Publish. All right, just see if you can see that now. So you weren't seeing anything at all? Oh my. I thought I published this from yesterday.
Sir, we saw the solutions, but not the link.
Ah, my apology, man. I thought oh, okay. Oh, I suppose that's why you're not as mad as me as I thought you would have been.
Yes.
All right, well, just check now. Are you seeing it?
Yes, sir, I'm seeing it there. I'm going to click on the link now.
All right, good. All right, well, that's it from me today. Let me just deal with the register. All right. So Adams, so Allen, Chavez.
Yes, sir.
Barrett. Barrett. Blake, both Blakes.
Yes, sir.
Sir. Yes.
Bruce.
Yes, sir.
Buckley. Burns.
Yes, sir.
Campbell.
Here, sir.
Copley.
Yes, sir.
Daly. Downer. Duplessis.
Present, sir.
Dwyer.
Yes, sir.
Ellis.
Here, sir.
Ferguson. Finley. Francis.
Yes, sir. Yes, sir.
Gibson.
Yes, sir.
Henry.
Excuse me, sir. Ferguson is here, sir.
Center.
Hewitt.
Yes, sir.
Jeffrey.
Yes, sir.
Sir Johnson, give up. Kamika.
Yes, sir.
Carr.
Yes, sir.
Leon.
Yes, sir.
Mason.
Yes, sir.
Merchant. Montague.
Yes, sir.
Phillips.
Here, sir.
Porter. Ramsey.
Here, sir.
Ready.
Yes, sir.
Reed. Christoph. Dario.
Present, sir.
Rose.
Yes, sir.
Russell.
Here, sir.
Shand.
Here.
Shirley.
Yes,
Yeah,
sir.
man. Sinclair. Okay. Smichael.
Present, sir.
Smith. Rajiv. Thomas.
Yes, sir.
Venna.
Present, sir.
And Watson. Oh, okay. Williams. All right, then Zhang. Okay. All right. Okay. So, folks, yeah, that's it. That's it. Yeah.
All right, sir.
A lot to think about. We will resume next Tuesday, all things being equal. By the way, I think most persons did fairly well with the lab test, especially those who did it on Thursday, since they had the benefit of information from Wednesday. But I suppose we'll flip this script next time, so the Thursday people will move to Wednesday, and let's see how well they do then, right? Have a good afternoon. Good rest of the day. Take care.
Sir, before you go, sir, so next week will be the next oral presentation, or tomorrow?
No. I have to complete the I have to mark the lab you are now doing.
Oh, okay then, sir.
Alright.
Excuse me, sir.
Uh-huh.
So, like, where can we like find like more questions to work on, like in the exam type, sir?
More questions.
Yes, sir. I feel like we're not doing enough practices on like examples for each topic, sir.
Okay. That can be arranged. Not a problem.
All right. Thank you.
That can be arranged.
Quick question, sir. As you mentioned, the lab we're currently working on, there has been some discussion regarding instructions given. I was wondering if any clarification was necessary, or as clear as is.
Go ahead, no? We're asking.
Like in terms of the
2 and the 1.5 and the 1.5, 1.5.
That's right, sir.
So we say you have to reduce it by those factors, eh?
Oh, okay, yes, sir.
All right, so the first exercise was to reduce it by a factor of 3. So in other words, you multiply it by 0.33, right? Multiply it by 1/3, eh?
Right.
The other two, if you note, I think there is a I'm trying to remember where the semicolon is placed. But you have it there as 2 and 1.5, and then 1.5 and 1.5. I think that's what you have there.
That's correct, yes.
Yeah, good. So what you're being asked to do is to reduce the active power in one instance by a factor of 2 or a half, yes, and the reactive by 1/1.5. So the first exercise, you reduced both by a factor of 3.
Yes, sir.
The other exercise, you're going to reduce active by 2, reactive by 1.5. And the other one is 1.5 and 1.5. So in each, for those two, you're reducing the active power, but you're keeping the scaled value of the reactive at 1.5. Any clearer? Sir Campbell, is that any clearer?
Yes, sir. It was Steve.
Okay. All right.
Sir, for that question, I
it
didn't
was
see
Burns.
it
Sorry. Pardon?
Sir, for that part of the lab, sir, I didn't see it to reduce. It just said to vary by a factor of 2, 1.5.
Sir, what did it say? It didn't say do the same thing as above.
No, sir.
You serious? Well, that would be I need to go look at that, man.
Sir, another thing for the...
Well, no, man, but you can't do that, man. I have to go look to make sure what you are saying is correct. And if what you are saying is correct, then I would have to adjust it. All right? So let's see what the instruction says now. So it's a repeat by scaling the case using the following factors. Repeat what you did in 2. That's what I said.
Sir, But the way how me did interpret that, sir, is I basically did the entire area by the two 1.5, then 1.5, then 1.5, sir.
No,
Yes,
but
sir.
you would have been doing the same thing.
Yes, sir, as what was in part 2. So that's how I interpreted the repeat part. So I just did what I did
Oh
for
my,
question 2.
All right, I hold up my hand. I hold up my hand because Mr. Burns actually wrote to me. Was it Burns or Smith? I think it was Mr. Smith. You're the one who wrote to me, right? Is he still there? All right, let me correct it. I apologize. I think I have misled the entire class. Mr. Venner, you're the one who corrected me a while ago.
Regarding what, sir?
Who said that they interpret it by just multiplying?
That wasn't me, sir.
Blake, sir.
Tevon?
Sir.
Okay, yeah. All right. The output will not, or what I'm aiming at, it will not impact you negatively. But Mr. Blake is actually correct. And I do apologize because somebody else had asked me about it and I gave them the megawatt and megavar. I'm now reading it again and the semicolons, because I was asking you where the semicolons. So now that I've opened the lab and looking at it, the semicolons are after each scale. Yes?
Yes, sir.
All right. So when you get it down to 17.6, all right? So after you have done step 2, what are you hearing me?
Yes, sir.
After you have done step 2, I have gotten it down to 17.6. That's the megawatt?
Right.
I think it was 50, just over 50 megawatts at first.
That's 53, sir.
Yes. And you scale it by 3, you get it down to 17.6. What I need you to do is to double it. So you're going to go to 35.
Yes, sir, that was what
and the megawatt will follow.
Right, yes, sir.
Okay. And then the 1.5 on top of that will bring you back to the original, which is 53.
Right, yes, sir.
And then you're going to do it another 1.5, which will bring you to about 78, if my memory serves me right.
Yes, sir.
And then the other 1.5 will bring you to just over 100 megawatts.
Yes, sir. That's what I was saying. I saw from the system.
Yes. So my apology. Thank you very much, Mr. Crasdale, for forcing me to open back the lab. All right, that's it.
Can we go to the other question now?
Pardon me?
Sir, I had another question, sir, for the examination, mid-semester.
Mr. Crasdale, look how long we talk about this, man, and you're just coming with this. All right, go on.
Because I just saw it. For question 4, sir. The same thing with the Bewley lattice diagram. Because you only asked for the voltage time diagram. I understand that.
All right. Listen.
Sir,
I'm not going to debate that one, you know. And let me tell you why. It is understood that the voltage time graph is generated from the Bewley lattice diagram. That's it.
Yes, sir, I understand that, but I was saying that I only drew the section that the user would be, or the viewer would be looking through. So I only drew that half of the Bewley lattice diagram.
But
to show
I
that
ask you for I ask you for the voltage on the line, and I ask you for the voltage on the cable.
Yes, sir, and I had that in the diagram, but you put a 0 and a question mark for the Bewley lattice. I drew the entire thing exactly as you had it in the solution, sir, but I didn't get a single mark for.
All right, Mr. Anaki. Let us see if you're going to benefit this time around.
Reconsider, sir, because that would just skyrocket my grade to the.
Skyrocket your grade.
Yes, sir.
Let us see. Let us see. I don't want to be unfair to you. So let us go there.
This doesn't honestly reflect my.
We understand that, man. We're not. I said that already, you know, and I said it not about you, but I said it about the class. Right? I think
Yes,
you're
sir.
all better than this, so you know I've already accepted that. So I'm looking at your paper now. So let's see if what you're accusing me of is accurate. All right, so I see that. I see that. Yeah, but I asked, but Mr. Anarchy, what are you querying? I have put there question sign and asking you for the Bewley lattice.
Sir, and the last page has a diagram with only the half that you asked about, sir. For the middle of the line.
And you keep saying the half that I asked about. You want me to read the question to you? It says,
yes, sir, so the line
sketch the voltage time graph for the voltage at the middle of the line and cable. You keep talking about the half I asked for. I didn't ask for half. I didn't ask for half, Mr. Anarchy.
I understand, but this drawing is for the line to cable. All right, sir. So I still think it's kind of unfair to get 0 marks.
Okay.
For the entire thing, so. But I understand.
But you never get 0 still, but yeah.
Sir, for the voltage time graph, I didn't get any marks for that.
I have a question.
Yeah, but we only have 2 more minutes now. Go ahead.
All right, sir.
Yeah, Mr. Anarchy, I will look back at it.
Okay, sir, thank you.
In terms of the table that you posted, right, on Schoology, for use of software and general readiness for a lab, is that the order that you're referring to?
Pardon me?
In terms of the table that you posted, right, after you have allocated marks for the labs, I'm seeing in the table where you have use of software and general readiness for a lab. Are you referring to the oral?
Yes. Yes.
All right, sir.
So now that you have done that, a grade will appear the next time I post it.
All right, sir.
All right then, folks. Have a good one.
You too, sir.
Cool.